Hi everyone! So in this video, we're going to be learning about a relationship between sine and cosine that's called the Pythagorean identity. So it sounds kind of fancy, but we'll see that basically the Pythagorean identity just comes down to the equation of the unit circle and then what we already know about sine and cosine in relation to the unit circle. So we'll get there in a little bit. First, I just want to do a warm-up problem. So once again, just practicing with evaluating sine and cosine. But the reason I'm doing this warm-up is so that we can then later use this example. So we'll be using this later on in the video. So as a warm-up, pause the video and evaluate sine and cosine of negative 2 pi over 3. All right, so negative 2 pi over 3. What is that going to look like as an angle? Well, that's the same thing as negative 2 times pi over 3. And so really that's telling us that we want to go pi over 3, so 60 degrees, twice, and we want to do that in the negative direction. So this would be negative pi over 3, approximately, something like this. And so negative 2 pi over 3 is going to be like that. So this is our angle of negative 2 pi over 3. So as we've seen in other examples, the way that we go about evaluating sine and cosine is by finding the terminal point, finding the x and y coordinate of the terminal point. And so this is going to give us, if we were to sketch a little triangle here, we'd see that we have a 30, 60, 90 triangle. So I'll draw it here. We can tell that this angle here is going to be pi over 6, whereas this angle here is going to be pi over 3. And again, I think, for the most part, you can usually just tell that based on, as long as you draw your picture somewhat accurately, you should be able to tell what is the shorter and longer side. The other way that you could verify that this is so this angle is pi over 3 because we're going negative 2 pi over 3, and that means that there's an additional pi over 3 left to get all the way to negative pi. And so that tells us that that top angle is pi over 3, and so the smaller angle must be pi over 6. And so we know that when we have our 30, 60, 90 triangle, we know that the shorter leg is 1/2, and the longer leg is square root of 3 over 2, and the hypotenuse is 1. And so we can use that to label the coordinates of our terminal point. So this time we're in quadrant 3, and that means that both the x and the y coordinates are going to be negative. And so the x coordinate is going to be negative 1/2. And then the y coordinate is going to be negative square root of 3 over 2. Okay, and so now we can use that to evaluate sine and cosine. So we know that sine is supposed to be the y coordinate of the terminal point. And so that's going to be negative square root of 3 over 2. And then to find cosine, and let me just scooch this down because that's kind of bugging me how close it is. And then to find cosine, we just take the x coordinate of the terminal point. So cosine of negative 2 pi over 3 is negative 1/2. Okay, cool. So that is just a reminder of evaluating sine and cosine. And again, we'll come back to this example a little bit later. Okay, so what is the Pythagorean identity? So like I said, this is going to be a relationship between sine and cosine. And I'll explain a little bit later what exactly the word identity means. But it's going to be a relationship between sine and cosine that we're going to come up with just by thinking about the equation of the unit circle and then the relationship between sine, cosine, and the unit circle. So first thing I want to do is just kind of label some point on this circle, just some random point x, y. So I'm just going to pick some point over here, and let's say that we have some angle theta. So we know that we can label this point with an x coordinate and a y coordinate, whatever those coordinates might be. Okay, so remember that the equation of the unit circle is x squared plus y squared is equal to 1. So what that means is that any point xy that lies on the unit circle must satisfy the equation for the unit circle. And so as we mentioned above, or as I mentioned a moment ago, the equation for the unit circle is x squared plus y squared is equal to 1. And we'll verify this with the example we just did earlier in the video in a moment. So any point that lies on the unit circle must satisfy the equation of the unit circle, which is that x squared plus y squared is equal to 1. Then there's another piece of information that we know. Additionally, if that point xy if that point is the terminal point of some angle theta, then we know that the x-coordinate is going to be equal to cosine of theta, and then the y-coordinate is going to be equal to sine of theta. And so all I'm going to do is basically combine these two equations, right? Or these kind of three equations. So we have x squared plus y squared is equal to 1. We also know that x is equal to cosine of theta and y is equal to sine of theta. So basically putting these things together, we're going to get the following equation. So I'm going to replace in our unit circle equation, instead of writing x, I'm going to write cosine of theta. So I'm going to say cosine of theta squared plus sine of theta squared. So I'm just replacing y with sine of theta is equal to 1. So again, it just comes right from the unit circle equation. It's just replacing sine and cosine with, or x and y with cosine and sine. And then there's a nicer way to write this. So instead of putting the square on the outside, this is kind of a new notation that you have to learn. Instead of putting the square on the outside, we're going to kind of tuck it in between the cosine and the theta. So I'm going to rewrite this as cosine squared of theta. And again, it means the exact same thing as what's written above. It's just notation. So it's just a different way of writing it. Basically, to avoid having to have so many parentheses, you can just put the square there and everyone understands that that means that it's the entirety of cosine and the entirety of sine that are getting squared. So this bottom equation that I wrote down, cosine squared of theta plus sine squared of theta is equal to 1, that is what we call the Pythagorean identity. So I'm going to scooch it down a little bit and label it as such. So this is the Pythagorean identity. And so this statement that is written down is going to be true for any angle theta. As long as the theta is the same in both of these instances. But for any angle theta, so we just kind of picked some random angle theta, right? So it could have been any angle. Everything that we did was just generic. It was true for any angle. And so this is our Pythagorean identity. So you might be curious, why is this called the Pythagorean identity? Well, basically, we came up with this by using the unit circle equation, but there's a different way we could have come up with it. So we could have done it instead by thinking about this right triangle. So if I were to draw a right triangle the way that we typically do in order to find the terminal point, we would have our side with a length of x and our side with a length of y. And then you could just use the Pythagorean theorem, right? So the Pythagorean theorem would say that x squared plus y squared is equal to 1 squared, or x squared plus y squared is equal to 1. And then we know also that x is cosine, y is sine, so it's the same idea. So really the unit circle equation and the Pythagorean theorem are basically the same. It's just kind of two different ways of saying the same thing. So this is the Pythagorean identity. This is really important. So we're going to learn a bunch of other things that are also referred to as identities, and I'll explain what that word means in a second. But we're going to learn a lot of different identities later on in the class. This is probably the most important one. So this is something that you're going to want to, I guess, have memorized, although I wouldn't really think of it as memorization. It just comes from the unit circle equation and what, the definitions of sine and cosine. So what does the word identity mean? An identity is basically an equation, but it's not an equation that like you solve. It's an equation that is true for all values of its variables. So just to kind of give like a side example, so an example of an identity unrelated to trigonometry might be something like this. So if you have x plus y squared, if you multiply that out, you would get x squared plus 2xy plus y squared. That is an identity because the left-hand side and the right-hand side are just kind of two ways of saying the same thing. And the left and right-hand side are going to be equivalent for all values of x and y. An example of something that is not an identity, so let me, right here, is an identity. An example of something that would not be an identity would be something like x squared is equal to 9. That is not an identity, right? That is only true for specific values of x. That is an equation, but it's like an equation that you would need to solve. Whereas this, you wouldn't solve this equation. This is just something where the left and right-hand side are the same. They're just different ways of saying the same thing. And so this is an identity. No matter what the value of theta is, this is always going to be true. You don't need to like solve this equation for theta. It is just true for any angle theta. So I want to take this identity and we're going to do a couple of practice problems using it. But the first thing I want to do is actually kind of verify that this identity works. And the way I'm going to do that is using our first example. So I'm just going to copy this and bring it down here. So for example, we can verify this identity with our earlier example. Okay, so we saw in our previous example that if you have theta is equal to negative 2 pi over 3, we saw that sine of negative 2 pi over 3, that came out to be negative square root of 3 over 2. And then we also saw that cosine of negative 2 pi over 3 came out to be negative 1/2. And so if we plug these values in, where if we do cosine squared of negative 2 pi over 3, I know that kind of looks like maybe a slightly confusing statement, but I'll explain what it means in a second. And then here we have sine squared of negative 2 pi over 3. We want to verify, is this actually equal to 1? Because if the Pythagorean identity is true, it should be, right? The Pythagorean identity says that for any angle theta, if you take cosine of theta and square it and do sine of theta and square it, add them together, you should get 1. So what do I mean? Like, how do we do cosine squared of negative 2 pi over 3? Well, remember that cosine squared, like this, it just means the exact same thing as taking cosine and then squaring it. So I'm going to leave it written like this, but when you're actually evaluating sine or cosine squared, the way you're going to do it is by finding the value of cosine and squaring it, and then finding the value of sine and squaring it. So we found earlier that cosine of negative 2 pi over 3 was negative 1/2. And then we found that sine of negative 2 pi over 3, we found that that was equal to negative square root of 3 over 2. And we're double checking that that in fact gives us 1. And so negative 1/2 squared, that would be equal to 1/4. Square root of, or negative square root of 3 over 2 squared, that's going to give us 3 over 4. right? Because square root of 3 squared is 3. And we do, in fact, on the left side, we get 4 over 4, and we know that 4 over 4 is equal to 1. So we have just verified that the Pythagorean identity works for this example. And this should feel kind of familiar, right? At the beginning of the quarter, or at the beginning of talking about the unit circle, rather, we were checking whether points lay on the unit circle, and it was exactly like this part of the process. And it makes sense that that's equivalent because the x and y coordinate on the unit circle are cosine and sine. So we're really just doing the same idea of verifying that a point lies on the unit circle. We're just kind of talking about it in a slightly different context. Okay, so I want to do a couple more examples. Basically, what we'll see is that because we now know the Pythagorean identity, it's going to be a way for us to, if we know the value of sine or cosine, it will help us to find the other trig functions. So I want to start with just kind of reminding you about the 4 quadrants and what they tell us about the values of sine and cosine, because this is just kind of a useful thing to be aware of. So this is stuff we already talked about, but I still think it's kind of worth rehashing. So, okay, let's say that you are in quadrant 1. So quadrant 1 would be this quadrant here. If you have an angle where its terminal point is in quadrant 1, we've already talked about how the x and the y coordinate are both going to be positive. And so what that tells us is that if you have an angle that is in quadrant 1, or whose terminal point is in quadrant 1, then what can we say about sine of theta, cosine of theta, and tangent of theta? And I actually asked you to think about this on one of your worksheets. So hopefully you did that and you already kind of have an idea of how you can answer this. So no matter what the angle is, if we're in quadrant 1, sine of theta is going to be positive. So actually I shouldn't say equal here. I'm just going to say is positive. And same with cosine, right? Cosine is also going to be positive because the x and the y coordinate, no matter where you are in quadrant 1, the x and y coordinate are both positive. And then tangent, well, there's 2 ways to think about it. One way is that you can do sine over cosine, and if sine and cosine are both positive numbers, of course you're going to get a positive number when you divide them. The other way you can think about it is if you eyeball the slope of this terminal side that I just drew, that's a positive slope, and so we know that that also verifies that tangent is positive. Okay, so quadrant 2, if you have an angle in quadrant 2, so the terminal point is going to have a negative x coordinate and a positive y coordinate. So maybe that is what your terminal side looks like. So if you're in quadrant 2, the y coordinate is positive, so that tells us that sine is going to be positive. And it tells us, and then the x coordinate is negative, and that tells us that cosine is going to be negative. And then tangent, well, if you take sine over cosine and you have a positive number over a negative number, that's going to always result in a negative number. And we can also verify that by looking at the slope of the blue line I just drew, or line segment I just drew. We can see that that has a negative slope. Okay, what about quadrant 3? Well, if you are in quadrant 3, then maybe you have a terminal point that looks something like this. So in quadrant 3, both the x and the y coordinates are negative. And so in quadrant 3, if the x and y coordinates are both negative, that's going to tell us that both sine and cosine are negative. And then if both of them are negative, so if you're doing a negative over a negative to find the value of tangent, well, that's then going to give you a positive number, right? Negative over negative is positive. And then if you look at the slope of this line segment I just drew, we can see that it has a positive slope, so that also agrees with what we know about tangent. And then finally, if we look in quadrant 4, so we have some kind of a terminal point in quadrant 4. In quadrant 4, the x coordinate is positive, the y coordinate is negative. So in quadrant 4, we have sine of theta. So sine is the y coordinate. The y coordinate is negative. So sine is negative. Cosine of theta is going to be the x coordinate, which is positive. And then tangent of theta, once again, this time we're doing a negative over a positive. So that's going to be negative. And then additionally, if you look at the slope of this line segment, the terminal side, we can see that it has a negative slope. So by the way, don't feel like you have to memorize this. There's like mnemonics that students sometimes use that kind of tells you in each quadrant what's positive and negative. I think it's kind of a waste of brain space to memorize all this, because really, as long as you know how to tell whether the X and Y coordinates are positive or negative, you can recover all this information. I just kind of wanted to go through it because it is something that we're going to be using in the next two examples. Okay, so first example says, suppose that sine of theta is equal to -1/5 and theta is in quadrant 4. Find cosine of theta and tangent of theta. So we're going to be using the Pythagorean identity, but first let's just go ahead and kind of sketch what theta might look like. We want to just kind of estimate roughly what theta could look like. So we know that we have an angle, so we know that sine of theta is -1/5. So what does that tell us about our angle? Well, it tells us that the terminal point should have a y coordinate of -1/5. So we can kind of estimate what that looks like by just remembering, okay, this is -1 down here, this is 0 up here, right? So what would -1/5 look like? It would be like 1/5 of the way down. So I'm just going to estimate, somewhere around here might be -1/5. And so what are the places where we could have a point on the unit circle where that is our y coordinate? Well, you could have a point here, right? That would be a y coordinate of -1/5. And then there could also be a point here. And we'll see that with the information we're given, only one of these two is going to be the correct one, but I'm just going to leave them both drawn there for a second. So again, we just sort of eyeballed, okay, -1/5 being the y coordinate, remembering that we have 0 up here and -1 down here. We just kind of eyeballed where -1/5 might fall in between those two. And it doesn't have to be perfect. It's just sort of some kind of an estimate. Trying to erase all this out without erasing other stuff. There we go. So which of these two is the correct picture? Well, we're told that theta is in quadrant 4. And so what that means is that it has to be this angle, right? This angle is in quadrant 3. So it can't be this one. I'm going to erase that one. So we don't actually know whether theta goes like this or theta goes like that. Either one of those could be the way that theta is measured, but it actually doesn't matter. And the reason it doesn't matter is because remember that coterminal angles have the same values for all the trig functions, because coterminal angles have the same terminal point. So we don't really care exactly how theta was measured. We just care about the terminal point of theta. That's all we need in order to answer this information. Okay, so let me label what we know here. We know that the y coordinate is -1/5, right? That's the information that we're given because we were told that sine was -1/5. And maybe let me write that down so if anyone's looking at their notes, they'll kind of see where we got this. And then I'm just going to put a question mark for our x coordinate because we don't know what that is. But let me just write down the fact that because sine of theta is equal to -1/5, the y coordinate of the terminal point of theta is going to be -1/5. Okay, so now we're ready to set something up that will help us figure out what cosine is. So basically we want to go back to our Pythagorean identity. And so the Pythagorean identity tells us that cosine squared of theta plus sine squared of theta is going to be equal to 1. And so because we know what the value of sine is, we can plug that in and then we can solve for cosine. And you might notice that you actually could set this up without even writing out the Pythagorean identity. You could just call the cosine, you could just call that x, and then you're basically just using the unit circle equation, right? You could just say x squared plus y squared is equal to 1, and then plug in -1/5 for y. It's equivalent. I'm just going to write it this way because, we just learned the Pythagorean identity. Okay, so we don't know what cosine is, so I'm going to leave that part written as just cosine squared of theta. But we do know the value of sine of theta, right? So sine of theta, we're told, is -1/5. And so I'm going to put in -1/5, and then we're going to take that number and square it. Okay, so I'm going to drop the color use because actually maybe I'll go back to green because it will get a little tedious. So we end up with cosine squared of theta plus, so -1/5 squared, that's going to be 1/25 is equal to 1. So let me just scooch this down a little. I think I underestimated how much space it would take for this. Oops. But yeah, what are we trying to solve for in this problem? We're just trying to solve for cosine. So we need to isolate cosine. And so the first thing we can do is move this 1/25 to the other side. So if we do that, we get cosine squared of theta is equal to 1 minus 1/25. And then 1 can be rewritten in terms of the common denominator of 25. So we can rewrite this as 25/25 minus 1/25. And so that tells us that cosine squared of theta is equal to 24/25. But we're not done. We still need to find cosine, right? This is cosine squared. And so what we want to do is take the square root of both sides. And so remember that when you take the square root of both sides, you have either a plus or a minus of the number of the square root of the right-hand side. So it's going to be plus or minus square root of 24/25. Because basically when you square a number, it always becomes positive. So you can't tell whether the original number was positive or negative. So in this case, we cannot determine yet whether cosine itself was positive or negative. And then this can be cleaned up a little bit. So we can rewrite this as the square root of 24/5, because square root of 25 is 5. And then we can even do a little better. So square root of 24, we can simplify this square root. So we can rewrite this as the square root of 4 times the square root of 6. And then the square root of 4 is equal to 2. So just kind of breaking this down a little bit. So we end up with plus or minus 2 root 6 over 5. Okay, so the last thing for us to figure out is it positive or is it negative? And so that's where our picture and the information about the quadrants comes into play. So by looking at our picture, because we're in quadrant 4, we can tell that the x-coordinate should be positive. And so we can conclude that cosine is actually positive. So we can select the fact that this must be positive because we're in quadrant 4. Okay, so now I'm going to come to the conclusion that cosine of theta is equal to the positive 2 times the square root of 6 over 5. But we still need to find tangent, right? The question asked us to find both cosine and tangent. But now that we have both sine and cosine, right, we know that sine is -1/5. To find tangent, we need to just divide them. So tangent of theta is going to be equal to sine over cosine. So sine, we already know, was -1/5. And then cosine, we just figured out, is 2 root 6 over 5. And I guess I still didn't really leave us enough space here. So I don't know why that thing keeps popping up. So now we can simplify this. So remember that when we have this same denominator, those numbers cancel out. And so we're left with -1 over 2 root 6. And then we can rationalize the denominator. So we can do that by multiplying this by square root of 6 over square root of 6. So if we do that, we're going to end up with negative square root of 6 divided by 12. Right, because square root of 6 in the denominator will have square root of 6 times square root of 6 is 6, and so we'll have 2 times 6, which is 12. And so that is our answer for tangent. So basically, this might look like kind of a complicated process, but again, we're really just using the fact that x squared plus y squared is equal to 1. It's just that we're writing it as cosine and sine because, that's what we just learned with the Pythagorean identity. But if you want to, you don't even need to use the Pythagorean identity on this. You can just use the unit circle equation because it's equivalent. It's the same thing. Okay, one more example. If you didn't already on the last one, I would recommend pausing the video and trying this one yourself. It's very similar. This time though, we're given cosine instead of sine, but we need to still find sine and then find tangent. Okay, so this time we're told that cosine of theta is equal to -1/3, and we want to find sine and tangent. So cosine being equal to -1/3, so cosine of theta equals -1/3 tells us that the x-coordinate of the terminal point is -1/3. And so we can use that to kind of make a rough picture for ourselves. So again, using the same kind of idea we did in the last one, we know that 0 would be here. We know that -1 would be there. And so -1/3 is going to be somewhere between. It's going to be, closer to 0, maybe somewhere like that. Does that look about right? Maybe a little further out. So -1/3 is going to be somewhere around like here. And so what would a point look like if its x-coordinate was -1/3? Well, it would either be here or here. And so we can figure out which point it is by just looking at the quadrants. We're told that theta is an angle in quadrant 3, and so that tells us that it has to be this point. And actually, let me just say one thing. I forgot to mention this on the last problem. I just want to quickly go back. So at this point when we decided whether it was plus or minus, so over here, if the answer had been the negative, that would correspond to the other possible point we drew at the beginning, right? So at the very beginning of this problem, we had two different possibilities. We said that either theta had its terminal point there or there. So if instead theta had been in quadrant 3, well, then the x-coordinate would have been -2√6/5. So it's not like some random, the plus or minus isn't some other random number that's just not true. It's just because it's not the right quadrant. So the other answer you get when you do this would correspond to the other place that the angle could have been if you weren't given that quadrant information. Okay, so our angle looks something like this. Again, we don't know how this angle is measured. It could be measured this way. It could be measured this way. It doesn't matter because all we care about is finding the terminal point. So this time we know the x-coordinate is -1/3, and we want to figure out what the y-coordinate is because the y-coordinate will tell us sine. Okay, so again, we want to set up our Pythagorean identity. So the Pythagorean identity says that cosine squared of your angle plus sine squared of your angle is equal to 1. And so we can substitute in what we know for cosine and then just leave the sine part. So we know that cosine of theta is -1/3. And so I'm just going to put -1/3, and we're going to take that and square it. And then we're going to have plus sine squared of theta is equal to 1. And I will drop the color coding again at this point. Okay, so -1/3 squared, that's going to give us 1/9. So we have 1/9 plus sine squared of theta is equal to 1. So we want to subtract this 1/9 over in order to isolate sine. So we would get 1 minus 1/9, but let's rewrite 1 as 9/9 to figure out what we get on that side. So 9/9 minus 1/9, that's going to be 8/9. So we have sine squared of theta is equal to 8/9. And so now we just need to take the square root of both sides and remember that we have a plus or a minus. So we have plus or minus square root of 8/9. So like in our last example, we can clean this up a little bit. We can rewrite this as the square root of 8/3. Square root of 9 is 3. And then we can actually break this number down a little bit. So square root of 8 can be written as the square root of 4 times the square root of 2, which is the same thing as 2 times the square root of 2. So that would be like the simpler way of writing this. So we have plus or minus 2 root 2 over 3. Okay, so how do we figure out which one it is? Well, again, that's where the quadrant comes into play. And so by looking at our picture here, because we're in quadrant 3, we can tell that the y-coordinate should be negative. In quadrant 3, both the x and y coordinates are negative. And that kind of goes back to what we talked about at the beginning here, right? In quadrant 3, sine and cosine should both be negative. So that tells us that our answer is going to be this one. So this is because we're in quadrant 3. So we can conclude now that sine of theta is equal to negative 2 root 2 over 3. And so just to remind you again what I said about the other problem, where is that positive 2 root 2 over 3 coming from? Well, that would be if we had the same kind of initial setup. So if we knew that cosine of theta was negative 1/3, but if instead we were in quadrant 2, right? We have this other possibility, you know, where's the other place where we have an x coordinate of negative 3? That would look like this. And so notice that for this one, the y coordinate would now be positive 2 root 2 over 3. So that's what the two possibilities, what they kind of look like on the picture. So last thing to do is figure out what tangent is. So now that we know sine and cosine, we can put them together to find tangent. So tangent is going to be sine, which is negative 2 root 2 over 3, divided by cosine, and cosine, remember, was negative 1 over 3. And so as has happened on others, we see that these denominators can cancel out. And so what we're going to be left with for tangent is actually just negative 2 root 2 over negative 1, which just simplifies to 2 times the square root of 2. So that is the value of tangent. All right, so that is it for this video. So like I said, really in this video, we didn't do too much that was new. We're just kind of talking about things in a slightly different way. But as I said on the last one, you can totally just use the unit circle equation. You don't need to write this as cosine squared plus sine squared, but you do want to know the Pythagorean identity. Like I said, we're going to be talking more about identities later on in the class, and this is one of the ones you definitely do want to know. All right, so I'll see you all in our next video.